Organic compounds. So chemists use the word organic differently than the people who run supermarkets. Originally, chemists divided compounds into two broad categories: organic, meaning it came from living organisms, and inorganic, meaning they came from the non-living environment. Organic compounds were much easier to decompose. You can burn them. They'll come apart more easily. But inorganic compounds are easier to make in the lab. They were not able to synthesize organic compounds in the early stages of chemistry. Today, we can synthesize organic compounds. Organic compounds are composed primarily of carbon and hydrogen. They may also contain oxygen, nitrogen, phosphorus, or sulfur, and sometimes a little bit of other elements, but they're going to be predominantly carbon and hydrogen. If there's no carbon in it, it's not an organic compound. Carbon is a nonmetal, and so the bonds in organic compounds between carbon and other elements are almost exclusively covalent. Carbon likes to form four covalent bonds. It could be 4 single bonds, 2 double bonds, a double and 2 singles, any combination to give you four bonds. It can do this with other carbon atoms or with other elements. And so the chemistry of carbon is unique and unusually complex because it often forms bonds with other carbon atoms and can make long chains of carbon atoms with other atoms on them, or different branched and ring structures. And so it's like a really cool building set that you can build all kinds of really neat stuff with. You can't make just this one particular thing. Here's some examples of carbon bonding. We've mentioned propane before. This is the structural formula for propane. The 3 carbon atoms have single bonds in a chain with each other, and then the hydrogen atoms are bonded to the carbons. You notice each of these carbon atoms has 4 bonds. Isobutane, cyclohexane, here the carbons form a ring, like they're playing Ring Around the Rosie. But again, each carbon has 4 bonds. Here's ethyne and ethene and acetic acid. We've mentioned this one before. This is in vinegar. This carbon atom has 4 bonds. It has a double bond with oxygen, a single bond with this oxygen, and a single bond with that carbon. So still with the 4 bonds. We can divide organic compounds into different categories. We are just like scratching the teeny tiny surface of the surface here. There's a whole 2-semester sequence on just organic chemistry. But we can take all of the compounds that exist, we can divide them into inorganic and organic, and then organic compounds can be divided into hydrocarbons and functionalized hydrocarbons. So you go to the store, and the connotation that organic has is that, oh, this must be better for me, this must be safer, right? Healthier. Okay, an organic chemical compound, I would say most of them are highly toxic, right? They may be natural, but that does not mean they're good for you. So hydrocarbons are compounds that contain only carbon and hydrogen, hence the name hydrocarbon. We interact with these on a daily basis. Oil, gasoline, liquid propane, natural gas, these are all composed primarily of hydrocarbons. They make good fuels because they burn nicely. So hydrocarbons can have all single bonds, or they may contain double or triple bonds, and the name suggests what is in it. So if it only has single bonds, they're called, as a group, alkanes. If they have a double bond, at least one double bond, it's an alkene, and at least one triple bond makes it an alkyne. So we have, for these hydrocarbon names, there's a base name, and that's not determined by the element. They all have carbon in them. It's determined by the number of carbon atoms. And then the suffix "-ane", "-ene", or "-ine" tells us what kind of bonds are present. Are there multiple bonds, and if so, what kind? So the base name has to do with the number of hydrocarbons. And we probably recognize these: dec for 10, none for 9, hex for 6, etc. It's all fine until we get down to 1, 2, 3, and 4. And these, I believe, have a more historical background. The prefix meth means 1, eth is 2, prop is 3, and bute is 4. So that can be a little bit difficult to remember. This is how I remember it to this day. Mom eats pickled bananas. And what does this suggest about Mom? She's gross. Or she might be pregnant, right? I don't think you can actually get pickled bananas. Could you pickle a banana? I don't know if you could. But it makes a great mnemonic: methyl ethyl propylbutyl, methane, ethane, propane, butane. Mom eats pickled bananas, 1, 2, 3, 4. And then the suffix has to do with the number or the types of bonds. So here we have methane. Meth prefix means 1. This has 1 carbon, and then it has enough hydrogens so that all the carbons have 4 bonds. Hydrogen is a little guy, it can only make 1 bond. Propane, the prefix prop means 3, so 3 carbons in a chain here, and enough hydrogens to go around. Then we've got butane and pentane. These have the prefix N on them, standing for normal, and that indicates a straight chain. This is like the tip of the iceberg, and the rest of the iceberg is all the other naming rules. And so there are rules for, well, what if it isn't a straight chain? But we don't have to talk about them in this class. So this one is ethene, eth meaning 2 carbons, and the ene tells us there's a double bond. So here since there's only 2 carbons, the double bond must be between those 2 carbons. And then this is only going to have 4 hydrogens because the carbons can only have 4 bonds. There's just no room for more hydrogens. Ethyne, 2 carbons with a triple bond. And these are common uses for these specific different hydrocarbons. So we said there were hydrocarbons and there were functionalized hydrocarbons. Functional group refers to a specific configuration of atoms and bonds that imparts a specific function to the compound. You could argue that double bonds and triple bonds between carbon atoms are functional groups as well. We look at a group of organic compounds that have the same functional group, and we call that a family. So methanol and isopropanol are both members of the alcohol family. And what they have in common is this OH functional group. That OH functional group gives them some similar functionalities. They will tend to undergo the same types of reactions. So this is methanol. So it's from methane, but then the ending is changed. Isopropanol, the prop, it means 3 carbons. So this one has 3 carbons, and it's got this ol function, the alcohol function. So these are the different families. I'm not going to give you questions about which is which, but I would just like to introduce them to you so that if you go on to organic chemistry, you will have seen them before. Alcohols have this OH group. The ethers have an oxygen between groups of hydrocarbons. Aldehydes have a carbon with a hydrogen and a double bonded oxygen on one end. The ketones are similar, but instead of a hydrogen here, they've got more carbons. Then we have carboxylic acids. Acetic acid is an example of this. They're kind of like a combination of an aldehyde and an alcohol because they've got this double bond with the oxygen, and then they've got this OH group. And then esters have that double bonded oxygen there, and then there's another oxygen thrown in here. And then the amines contain nitrogen instead of one of the carbons. So that's a very brief introduction to families of organic compounds. Okay, so draw the structural formula for nonane. This is something that you should be able to do. What does the prefix non mean? No. It means 9. So this is going to have 9 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the sort of math that's required in organic chemistry. Counting, usually you don't have to count much past 10. And then each of these carbons has to have 4 bonds. And the thing that's bonded to the carbon, other than the carbons indicated by the 9, is going to be hydrogen. And if you're drawing this with me, you'll recognize that drawing structural formulas for compounds like this gets a bit tedious, doesn't it? That's a lot of H's. The molecular formula for that would just be the list of how many carbons and how many hydrogens. And so there's 9 carbons, C9, and there'd be 20 hydrogens. You can count, and you'll see that I'm right. So that's the sort of question that could end up on an exam, or I could give you a picture like this and ask you what its name is. What if I took out 2 of these carbons and put a double bond there? What kind of a thing would that be? Nonene. We take nonane and we change the ending from ane to ene. So you should also be able to recognize something like that. You count the number of carbons. If there's a double bond, the ending is ene. If there's a triple bond, it's ine. It would be nonine.
How do we know that the double bond is right here?
Well, you wouldn't. There's more complicated rules to the naming. This would actually be 2 nonene, but we're not learning those rules. So if I asked you to write or draw a structural formula, say for butene, so this prefix but means how many? 4. Mom eats pickled bananas, it's 4. So 4 carbons. And butene is not a specific enough name that you would only get one structure. There's a couple of different possibilities. I wouldn't expect you to have a particular one. I would accept any that fit this description. So the ine tells us triple bond. So you could put the triple bond here, or you could put the triple bond between the first and the second carbon. It wouldn't matter to me. And then you fill in with hydrogens. So why are the carbons in the middle not getting any hydrogens? They already have 4 bonds. This carbon has this 3 in the triple bond and 1 single bond over here. There's no room for hydrogens on there. This is the sort of question that I would not ask you on an exam, but it could show up on homework. To which family does this compound belong? I would expect you to need this chart. So here we've got this carbon double bonded to oxygen, and then look what's attached to this carbon. It's other carbons, right? So when we look over here, there's several that have the C double bond O. This one's got oxygen, that one has oxygen, it can't be one of those. Here, this carbon is bonded to other carbons. This carbon is only bonded to one other carbon. So this is the winner, that's a ketone. So this is a member of the ketone family. Again, I wouldn't ask you to do that on an exam. Any questions?